Greetings, Chem 110H, Dr. Bevilacqua here. I wanted to go through homework 4, question 7 on the isothermal and isobaric expansions of an ideal gas. In the first part, in the isothermal expansion, delta T is equal to 0. That's what isothermal means. And this is in a piston, and it has good seals. It doesn't leak, so delta Ng is equal to 0. And we're told that the volume doubles. We can use the relationships from the ideal gas equation to show that the pressure decreases by a factor of 2. The first part asks us for the heat involved in the process, and in order to get this, I'm going to use that delta E for an ideal gas is equal to 3/2 NR delta T. Because delta T is 0, we know that the delta E value is equal to 0. Delta PE is always 0 for an ideal gas because there's no bonds. Therefore, we can go ahead and first write down the answer for part F, and that is that delta KE must be equal to 0. Now, in an effort to get Q, we can set delta E equal to Q plus W, and now we know that Q is equal to minus W. So if I can get W, I'll know Q. And in order to get W, I'm going to use that W is equal to minus the integral of P dV. But P is not constant in this process. P is decreasing. And so I can't pull it out in front of the integral, but I can substitute from the ideal gas equation this form for P equal to nRT over V. And when I do that, I can pull the nR, and T is constant, it's not changing, out in front of the integral, and do the integral of dV over V from an initial volume to twice that value. And when I go through and do this, the integral of dV over V is the natural log of V. And when I evaluate it from 2V to V, I end up with this expression. And the V's cancel when I use the proper mathematics for logarithms, and I'm left with W equals minus nRT, the natural log of 2. Going back here, because Q is equal to minus W and W is minus, I now know that Q is positive, and it's going to equal positive nRT, the natural log of 2. Here's the Venn diagram for this process. Delta E is equal to 0 for the reasons we said over here. And so we see that even though it's equal to 0, stuff is happening with Q and W, but it's happening in such a way that their sum is 0. Q is going into the system, and W is coming out. Let's go on now and move on to the next part of the problem. The next question is about what happens to the velocity, and I'm also going to tackle what happens to the momentum at this part. Velocity is given by the square root of 3RT over molecular weight, and momentum is equal to mass times this velocity. We're told that the temperature is constant and that the gas does not leak, so we know that neither change. So the velocity is constant and the momentum is constant. Now let's go on and think about the frequency of the collisions. And in order to do this, it's helpful to think about the piston in two different aspect ratios. I'm first going to use a high aspect ratio, in which I kind of have a long and skinny piston, and it starts out with length L, and it increases to 2L because the volume doubles. We can look at the area when we have the initial state. It's equal to 2 pi r squared, which is the area of the top of the piston and the bottom. And then we have the area that's contributed along the length of the piston, which is given by the circumference, 2 pi r times the length L. The final area has the same 2 pi r squared contributed by the top and the bottom of the piston, which hasn't changed. But the area that's contributed along the length of the piston has doubled. And so now it's 2 pi r times the new length, 2L. Let's go in and look at what happens with the pressure. We know that the pressure is going to decrease 2 times from what we saw on the first page. And let's see where this comes about at the microscopic level. Well, we see, given the area here, that the area almost doubles. Most of the area comes from this term. The contribution that comes from the top and the bottom is small. Because this term doubles, the area almost doubles, but not quite. We can then look at the top term in the numerator, the force. As we talked about this, we can consider this coming from momentum transferred per collision times the frequency of collisions. In order to think about the frequency term, I've got a little equation here that the distance traveled is equal to the velocity times t, or v is equal to d over t. And t can be thought of as inverse frequency, or frequency is inverse time. If we rearrange this little equation and solve for f, we get that f is equal to v over d. Given the aspect ratio of this piston, most of the molecules are going to be traveling left to right, and that distance doesn't change at all. And we also saw that the velocity doesn't change. So for those guys, for those molecules moving left to right, the frequency doesn't change at all, the momentum doesn't change, and so the force doesn't change. But for some of the molecules, they'll be traveling up and down, or maybe on the diagonal. And for those guys, the distance doubles or increases. And here, that causes the frequency to go down. And so that causes a contribution to F to cause it to decrease just a little bit. The fact that the denominator does not quite double is compensated for by the fact that the numerator goes down just a little, so that overall the pressure goes down 2 times. Now let's go ahead and consider what happens with the other aspect ratio of the piston. This is a very wide aspect ratio. The volume needs to double, and so L again doubles to 2L. The change in the surface area is very slight in this particular case, because most of the area comes from the top and the bottom, and that doesn't change during the expansion. Here's the equation for pressure. The denominator, A, as we just said, has almost no change, but still there's a slight increase from the contribution that comes along the outside of the piston. If we look at the numerator, force, this term almost decreases twofold. On the previous slide, we saw that frequency is equal to velocity over distance. Velocity doesn't change. Most of the molecules will be moving up and down. Their distance has doubled from L to 2L, and so the frequency of their collisions decreases twofold. But some of the molecules will be moving left to right or on the diagonal. So there isn't a true twofold decrease, but there's an almost twofold decrease. Yet the pressure still decreases twofold because the denominator increases slightly. So we see once again that the pressure exactly decreases by a factor of 2, just like we know that it must from the ideal gas equation. And then the last question that is asked on this particular problem is what happens to the density of the gas? Well, we can write down that the density of the gas is equal to N over V, or that the final density is equal to N over V final, and the initial density is equal to N over V initial. I can use N because the number of gas molecules doesn't change. We rearrange this equation, and we see that final over initial density is equal to initial over final volume, which is equal to 1/2. Or in other words, the density of the gas decreases by a factor of 2 when the volume doubles. Let's go on now to the second part of the question and consider an isobaric expansion of an ideal gas, or a constant pressure. At constant pressure, delta P is 0. Again, delta Ng is 0. We know that the volume doubles, and using the relationships in the ideal gas equation, we can reason that the temperature must double, or that the system gets hotter. Let's look at the pieces that go into the various parts of the question. And the first is we're actually told that the heat is positive in the problem, so we don't have to solve for this. Delta E is equal to 3/2 nR delta T. Because the temperature doubles, T2 is equal to 2 times T1, or we know that delta E doubles, and it's equal to 3/2 nR T1. We can then take a look at what happens with the change in kinetic energy. Well, delta E is all kinetic energy. Again, ideal gas has 0 potential energy, so if delta E doubles, then delta KE is equal to 2, or Ke doubles. We can then go ahead and sketch out our Venn diagram. Delta Ke increases 2 times, delta Pe is 0. And where does this come from? Well, there's negative work in this process. Because it's isobaric, we can pull out P in front of the integral and simply have our standard minus P delta V. V2 is twice V1, so we end up with minus P V1. And because delta Ke increases by a lot and W is going out of the system, Q must be a large value. And so I've depicted that here, a large positive value, and I've depicted that here with a big arrow with Q going into the system. So now I'd like to consider the other parts of this problem. In terms of the velocity, it's given by root 3 RT over molecular weight. We're told that the temperature doubles, molecular weight is constant, so the velocity increases by the square root of 2. The same must be true for the momentum. It increases by the square root of 2. Let's now consider what happens with the frequency of collisions. We'll first take the piston with the long aspect ratio, and we'll just look at the final state, which is 2L. Here's the equation for pressure. As we saw earlier, the area almost doubles. Because this is isobaric, the force must almost double as well. Let's see where this comes from at the molecular level. We can think about force as momentum transferred per collision times frequency of collisions. Momentum transferred increases precisely by the square root of 2. How about the frequency of collisions? Again, this is given by velocity. That increases by the square root of 2, divided by distance. Most of the molecules will be traveling left to right, and their distance won't change. And so a few, however, will be traveling up and down. And so if we look at what happens with the frequency of collisions, we have square root of 2 over a nearly constant, but slightly increasing denominator. And so the frequency of the collisions almost goes up by the square root of 2. When we multiply these two terms together, we get something that almost doubles. And when we divide that by the area, which almost doubles, we can then understand why the pressure is constant in this particular aspect ratio. So let's finish by considering the wide aspect ratio. Here's the final height of 2L, the equation for pressure, and let's look at each of the pieces. We know for this aspect ratio the area increases only very slightly. Force comes from momentum transferred, which increases precisely by the square root of 2, times the frequency of collisions. This is equal to velocity over distance. Velocity increases by precisely the square root of 2. The distance traveled by gas molecules that are moving up and down doubles. Those few that are moving left to right, there's no change. And so, on average, the distance almost doubles. Because of that, we can then look at the frequency of collisions. For those gas molecules moving up and down where d doubles, the frequency goes down by 1 over the square root of 2, which comes from the square root of 2 over 2. But because the distance doesn't quite double, then the frequency doesn't quite go down by 1 over the square root of 2. And when we multiply that by the square root of 2, we see that the numerator here doesn't quite stay constant. It has a very slight increase. And that very slight increase balances perfectly with the very slight increase in the area, such that the pressure stays constant, as it should for an isobaric expansion. And then in the last part, we're asked to consider the density. Because the volume doubles, just like in the isothermal expansion, the density goes down twofold. Thanks for listening.